Welcome to the Perceptive APC online tutorial for parallel coordinates. In this video we'll take you through the steps involved in setting up and configuring a parallel coordinates plot in the Perceptive APC software suite. DataMV is being used in this demonstration, but the steps are the same in any of the Perceptive APC software products. In this case we're going to use a continuous data file. To load it we go to Data, Continuous and then Files in the Explorer tree, double-clicking on the dataset of choice. This will open a continuous data table. From here, a parallel coordinates plot can be created by selecting the signals of interest, and from the right-click menu, selecting Graphical Displays and Parallel Coordinates Plot. Alternatively, you can create a blank parallel coordinates plot by clicking on the Parallel button in the main toolbar. There are three main areas to a parallel coordinates plot: the chart area, the signal definition area, and the set definition area. I'll now go on to describe each of these in turn. Parallel coordinates plots are set up in a very different way to traditional trends, and this makes them great for identifying relationships in your data and pinpointing different operating regions within a process. Each vertical axis in the charts represents a different signal scaled from its lowest to its highest value, with each horizontal line representing a different sample in the data set that passes through the relevant value points for that signal's observation value. The thick green line represents the observation values for the current cursor position. We're now going to configure the chart area to show all the information we want by selecting Properties from the chart's right-click menu. In this case, we're going to select Auto Update to automatically update the chart area every time we make a change, and Descriptions to show the tag descriptions at the top of the chart area. Another useful tool is the Show Statistics Bars option. This generates a green spot at the position of the mean value for each signal, yellow bars representing the areas that are between 2 and 3 standard deviations from the mean, and red bars representing areas that are 3 standard deviations or greater from the mean. In this example, the main signal of interest is the product outlet temperature. Therefore, we're going to move it to the left-hand side of the plot area by clicking on the signal ID and dragging it to the position of choice. More signals can be added in one of two ways, either through the right-click menu on the main plot area and choosing Select/Order Signals, selecting the signals you want to include from the resultant dialog and adding them to the list, or by going to the data table and dragging the signals of interest onto the plot area. Once all the signals are in the plot, they can be reordered by clicking on the signal ID and dragging it to the position you want them to be in. In this case, we're putting all the product temperatures in process order. Now that we have finished configuring the plot area, we can move on to the Signal ID section. Each Signal ID has its own right-click menu that allows you to perform a number of actions. These include Invert Min-Max, which reorders that signal's vertical axis so that the minimum value is at the top and the maximum value at the bottom, and Trend, which brings up a trend of the selected signal over the analysis range. The final area of interest is the Sets definition area. A set is a section or sections of data that fall within a user-specified range. To create a set, right-click on the Set area for the signal of interest and select Set Limits from the right-click menu. This brings up the Configure Signal Limits dialog, where we can set the signal values active and then select our limit configuration. This is either the mean plus or minus 1 standard deviations, plus or minus 2 standard deviations, plus or minus 3 standard deviations, or the maximum and minimum values in the analysis range, which is what we're going to use in this case. The resultant set covers the entire data range, but we're only interested in the periods of operation when the product outlet had a high temperature. Therefore, we click on the limit bar at the bottom and drag it up until the set covers only the range of interest. Now only the observations that corresponded to a high product outlet temperature are coloured blue. Now we want to create a new set that covers periods of operation with a low outlet product temperature. To do this, we right-click on the set area and select New Set. This will create a second set, in this case coloured green. Right-clicking on the green set area for the outlet temperature and selecting Set Limits allows us to set the limits as we did for the high temperature range. As we're only interested in low product temperatures for this set, we click on the upper Set Limits bar and drag it down so that the set only covers the periods of operation with a low product temperature. We can now see differences in operation across all the signals for high and low temperature product. It would appear that there were periods of operation with high outlet product temperature when the T2 cold-in temperature was high, and periods of operation with a low outlet product temperature when the T2 cold-in temperature was low. Each set can have limits applied to more than one signal at a time. Therefore, we can use additional limits applied to the T2 cold-in temperature to achieve greater differentiation between the high and low product periods of operation. Now we can also see increased separation for the sets when looking at the T3 to T4 product temperature. Sometimes removing a set aids clarity for particular analysis. This can be done by right-clicking on the set you want to remove and selecting Hide. Repeating this will bring it back again. The data ranges for each signal in a given set are shown in the set area. For signals where a limit has been set, the high and low values are separated by a double arrow. For signals where no limits have been set, the high and low values for that set are contained within square brackets. We can change a set's colour by right-clicking on the set of interest and selecting Edit Colour. This brings up a dialog box where we can click on the colour we want to use and then select OK. In this case, we'll set it back to blue. We can also generate a distribution chart for any selected signal. This is done by right-clicking on the set of interest and selecting Distribution Chart. This generates a histogram that shows not only the distribution of all the data, but also a colour-coded distribution for the selected set. Finally, we're going to export a set to a signal. In this case, we're going to have to create a new signal. In order to do that, we're going to go to the Data table and select the Product Outlet Temperature signal. The right-click menu for the selected signal has the option of Applied Transform. In the Apply Transform dialog, we're going to select the action as Copy. This will copy all the values in the selected signal into a second signal. In this case, we're creating an entirely new signal with the signal ID of 2000.me and a descriptor of high set. We can now see that 2000.me has been added to the data table and populated with the same values as the outlet product temperature signal. Returning to the parallel coordinates plot, we now right-click on the set we want to export, select Export Set from the menu, and then 2000.me from the signal list. In the data table, we can now see that 2000.me has been repopulated with values of 0 for observations that are not in the selected set, and values of 1 for those observations that are. Trending this signal allows us to see the periods of operation that resulted in a high product outlet temperature. That concludes the Parallel Coordinates online tutorial. For more information on perceptive engineering, please visit us at www.perceptiveapc.com or follow us on Twitter @PerceptiveAPC.